Welcome to today's paper reading. Today's paper is titled Smaller, Weaker, Yet Better, Training LLM Reasoners via Compute Optimal Sampling. This paper was published on the AR14 preprint by Hritik Bansal and colleagues from Google DeepMind. In this study, the authors explore the effectiveness of using synthetic data from both strong and weak language models, LLMs, for training advanced reasoning capabilities. They examine the trade-offs between generating data from a stronger but more expensive model versus a weaker but cheaper model, focusing on metrics such as coverage, diversity, and false positive rates. The authors then fine-tune LLMs using data from these models in various settings, including knowledge distillation, self-improvement, and a novel weak-to-strong improvement setup. Their findings indicate that models fine-tuned on data generated by weaker models consistently outperform those trained on data from stronger models across multiple benchmarks and diverse fine-tuning paradigms. This challenges the conventional approach of relying on strong models for synthetic data generation, suggesting that weaker models may offer a more compute-optimal strategy for training advanced LLM reasoners. Figure 1 summarizes the results of fine-tuning language models, LLMs, on synthetic data generated by stronger but more expensive, SE, models versus weaker but cheaper, WC, models. In Part A, models fine-tuned on Gemma 2-9b data show better performance across various fine-tuning paradigms, including knowledge distillation, self-improvement, and weak-to-strong improvement, on the math dataset. This suggests that using WC models for data generation is more compute-optimal. In Part B, fine-tuning with data generated by the Gemini 1.5 Flash model consistently outperforms that generated by the Gemini 1.5 Pro model, indicating that cheaper models can yield superior results when matched in price. These findings challenge the conventional reliance on SE models for synthetic data generation, advocating for the use of WC models to train advanced LLM reasoners. Language models, LLMs, have shown significant capabilities in reasoning tasks, primarily due to their extensive training on large datasets of problem-solution pairs. However, the process of collecting such data from humans is both expensive and time-consuming. Recent studies have shown that synthetic data generation using LLMs themselves can be a more scalable and efficient solution. This synthetic data has been shown to outperform data generated by humans in several studies. In this paper, the authors explore an alternative approach to sampling, focusing on using weaker but cheaper, WC, models rather than stronger but more expensive, SE models. This approach aims to achieve higher coverage and diversity in the generated data, albeit with a potentially higher false positive rate, FPR. The authors demonstrate that this method can lead to more compute-optimal training of language model reasoners. Figure 2 illustrates the approach of using a fixed sampling budget to generate data for training language model reasoners. It compares generating fewer samples from a stronger but more expensive model, SE, versus more samples from a weaker but cheaper model, WC. The figure highlights that using the WC model can solve a wider range of problems and produce more correct solutions per question. The utility of these synthetic datasets is evaluated in various supervised fine-tuning setups, showing that training with WC-generated data consistently outperforms training with SE-generated data. The training dataset, denoted as D, consists of n pairs of reasoning questions and final answers. To improve models for reasoning, synthetic data is generated by sampling multiple solutions for each question at a non-zero temperature. This synthetic dataset, D, includes case samples of reasoning chains and final answers for each question. Incorrect solutions are filtered out by comparing the generated answers to the gold standard answers. The remaining data is used to fine-tune a model to maximize the probability of generating correct reasoning and answers. Evaluation metrics include coverage at, which measures the fraction of questions with at least one correct solution, diversity at, which averages the number of unique correct solutions per question, and false positive rate, FPR, which indicates the percentage of solutions with incorrect reasoning but correct final answers. In this section, we discuss the concept of compute-matched sampling and training. At a fixed computational budget, we can either generate more samples from a weaker but cheaper model or fewer samples from a stronger but more expensive model. The sampling ratio between these models is determined by the ratio of their parameters. We explore three fine-tuning setups: Student LM, which uses knowledge distillation, WCLM, which focuses on self-improvement, and SELM, which introduces a new paradigm called weak-to-strong improvement. These setups aim to compare the utility of data generated under a fixed budget and to understand the effectiveness of different fine-tuning paradigms. Table 1 provides a summary of the supervised fine-tuning setups used in the study. The setups include fine-tuning a student LM, a weak cheap WC LM, and a strong expensive SELM. Each setup employs different fine-tuning paradigms based on the source of the synthetic data. The paradigms include knowledge distillation, self-improvement, and a novel weak-to-strong improvement. The table highlights the comparison of synthetic data utility from WC and SE models, showing how the different setups and paradigms affect the fine-tuning process and the resulting model performance. In this experimental setup, the authors utilized two primary datasets, Math and GSM-8K. Each dataset contains 7,500 math problems, with evaluations conducted on 500 problems from the math test split and 1319 from GSM-8K. For data generation, pre-trained GEMMA 2 models, specifically GEMMA 2-9b and GEMMA 2-27b, are employed. These models generate solutions using 4-shot and 8-shot prompts respectively, with varying sampling budgets to produce different numbers of candidate solutions per problem. The model fine-tuning process involves the GEMMA 7b model, which is fine-tuned on data from GEMMA 2-9b and GEMMA 2-27b, with additional setups for WCLM and SELM. The fine-tuning also includes human-written solutions as a baseline for comparison. Figure 3 presents an analysis of synthetic data for the math dataset, focusing on the coverage, diversity, and false positive rates of the GEMMA 2-27b and GEMMA 2-9b models at two different sampling budgets. The coverage comparison highlights the efficiency of solution generation under fixed sampling constraints. The diversity comparison evaluates the variety of solutions produced by each model. Lastly, the false positive rate comparison assesses the accuracy of the reasoning paths generated by the models. These metrics collectively provide insights into the performance and reliability of the synthetic data generated by the GEMMA models. In this section, we present the results of our experiments comparing the WC and SE models across various metrics. First, in synthetic data analysis, we found that the WC model outperforms the SE model in terms of coverage and diversity, although with a higher false positive rate. Specifically, the WC model's coverage is 11% and 6% better at low and high sampling budgets, respectively, and its diversity is 86% and 125% higher. However, the false positive rate for WC-generated solutions is 7% higher on the math dataset and 2% higher on GSM-8K. Moving on to compute optimality results, we observe that fine-tuning with WC data consistently leads to better performance than with SE data, both in terms of accuracy and generalization capabilities. This trend holds even when varying the dataset size, as smaller datasets generated by the WC model still outperform those from the SE model. Finally, our ablation studies further support the benefits of the WC model, showing that compute-optimal sampling and maintaining both high coverage and diversity are crucial for training strong reasoners. Figure 4 presents the supervised fine-tuning results on the math dataset, comparing the performance of various language models, LMs, fine-tuned on synthetic data generated by the WC, GEMMA 2-9b, and SE, GEMMA 2-27b, models at a fixed sampling budget. The key observation is that training with samples from the WC model consistently yields better results than those from the SE model, highlighting the superior performance of the WC model and generating effective training data for the math dataset. Figure 5 presents the supervised fine-tuning results on the GSM-8K dataset, comparing the performance of various language models, LMs, fine-tuned on synthetic data generated by the WC, GEMMA 2-9b, and SE, GEMMA 2-27b models. The results indicate that training with samples from the WC model consistently produces stronger reasoners than those trained with SE data. Notably, the false positive rates, FPRs, are significantly lower for the GSM-8K dataset as compared to the math dataset. Additionally, the study highlights the ongoing challenge of automatic verification of reasoning steps, which can still contain errors, as noted by Lightman et al., 2023. Figure 6 illustrates the generalization results of models trained with synthetic data from the math dataset at high sampling budgets on the functional math dataset. The key finding is that models trained with WC data consistently outperform those trained with SE data. Specifically, Gemma 7b fine-tuned with WC data shows significant relative gains at high sampling budgets, indicating enhanced generalization capabilities. Figure 7 illustrates the impact of dataset size on the performance of fine-tuned language models, LLMs, using synthetic data from WC and SE models. The results show that training with WC data consistently leads to better models compared to SE data, regardless of the dataset size. This advantage is quantified by relative gains ranging from 5.8% to 6.5% across different values of K. Furthermore, the study highlights that using WC data enhances the generalization capabilities of the models over those trained with SE data, reinforcing the notion that WC data may be more compute optimal for various tasks and setups. Figure 8 compares the performance of models trained with number-matched and compute-matched sampling from the WC model. The results show that models trained with compute-matched WC data outperform those trained with number-matched WC data and SE data. This suggests that future comparisons between synthetic data from weak and strong models should be made in the compute-matched regime to achieve better performance. Figure 9 illustrates the impact of coverage and diversity on training strong reasoners using the WC model. The figure compares the performance of training language models, LLMs, with synthetic data generated under three conditions: A. Collecting only one solution per problem, resulting in low diversity and low coverage; B. Collecting 30 solutions per problem, leading to high diversity and high coverage; and C. Collecting 30 solutions per problem but retaining only one correct solution, which maintains high coverage but with low diversity. The results indicate that both high diversity and high coverage are beneficial for training effective reasoners. In this section, the authors explore the effectiveness of data sampling from weaker state-of-the-art language models, SOTA LLMs, compared to stronger ones. They use the pricing per output token as a proxy for compute-matched sampling, noting that Gemini 1.5 Pro costs $10.50 per million tokens, while Gemini 1.5 Flash costs 30 cents. This leads to sampling one solution per problem from Pro and 35 from Flash. The authors then perform knowledge distillation on Gemma models 7b, 9b, and 27b, using synthetic data from these models. They find that fine-tuning with data from the Flash model outperforms that from the Pro model, achieving relative gains of 31.6%, 14.4%, and 10.9% for the respective models. Additionally, they investigate training with less expensive data by sampling 5 solutions per problem from the Flash model, which is 7 times more economical than generating one solution from the Pro model. This economical approach also yields performance gains, demonstrating that price-matched sampling from weaker SOTA LLMs can produce superior reasoners compared to stronger models. Figure 10 compares the fine-tuning performance of Gemma models 7b divided by 9b divided by 27b, using synthetic data from Gemini 1.5 Pro and Gemini 1.5 Flash. The results show that data generated by the Flash model consistently outperforms that from the Pro model, achieving significant relative gains of 31.6%, 14.4%, and 10.9% for the 7b, 9b, and 27b models, respectively. This performance advantage is attributed to the higher coverage of the Flash model, which is 81%, compared to 61.1% for the Pro model. Additionally, the Flash model's data is more cost-effective, providing superior results even at a reduced cost of 0.15 times compared to the Pro model. The authors discuss the potential for training reasoners through sampling from WC models to be more compute optimal, especially relevant for future WC and SE models. They surveyed 17 language models that meet specific criteria, including model size and performance on the math dataset. The analysis shows that smaller language models, 1B to 9B parameters, are improving more rapidly in reasoning performance compared to larger models, 20B to 80B parameters. This trend is attributed to factors like enhanced pre-training data and knowledge distillation techniques. As the performance gap between small and large models narrows, the findings of this study are expected to become increasingly relevant in the future. Figure 11 illustrates the performance variation of open language models on the math dataset over time. The trend lines fitted to the data points show that smaller language models, 1B to 9B parameters, are improving at a faster rate compared to larger models, 20B to 80B parameters. This rapid improvement in the quality of smaller LMs suggests that using these models for training strong reasoners will become increasingly relevant in the future. The steeper trend line for small LMs indicates their growing capability in reasoning tasks, which is attributed to enhanced pre-training data quality and knowledge distillation techniques. The ability to solve reasoning tasks has been a long-standing goal in artificial intelligence. Large language models, LMs, trained on vast amounts of data have shown significant success in tasks like math and coding. Several methods have been proposed to enhance the reasoning capabilities of LMs, either through prompting or fine-tuning. In this work, the focus is on fine-tuning LMs with task-specific datasets to build strong reasoners. This approach aligns closely with the widely adopted STAR method, which uses synthetic data from LMs to elicit strong reasoning capabilities. Within the fine-tuning paradigm, various works have improved reasoning using synthetic data, focusing on knowledge distillation from expensive LMs or self-improvement. Our approach explores the utility of synthetic data from weak but cheap LMs for training strong reasoners via knowledge distillation and self-improvement. Our weak-to-strong improvement paradigm, where a strong model is trained with generations from a weak model, is related to prior work that studies the ability of a strong LM to learn from weaker data. However, our aim is to further enhance the strong model's capabilities through compute-optimal sampling, which has not been explored in previous work. In this study, the authors present a framework for compute-optimal sampling from weak but cost-effective language models, LMs, for reasoning tasks. They demonstrate that, given a fixed sampling compute budget, repeated sampling from a smaller model can yield higher coverage and diversity compared to using a stronger but more expensive model. Additionally, their empirical results indicate that fine-tuning LMs with data derived from the smaller model consistently outperforms fine-tuning with data from larger LMs, all within the same compute budget. These findings lay a solid groundwork for training LM reasoners, particularly as the performance gap between small and large LMs is expected to diminish over time. Thank you for watching.